Hello, I'm Jose Tinoco Carrillo, and this is my evidence to video for the Design of Bioseparation Strategies course. As an introduction, our challenge consisted on helping GIA brands purify a lactic acid fermentation broth produced from stevia bagasse by the use of Lactobacillus plantarum bacteria. This fermentation broth has a lactic acid concentration of 35 grams per liter, and we seek to purify it up to the 88% purity level. To do this, we sized up the bioprocess and designed like all the steps necessary to achieve the desired purity level. Um, GIA Brands produces 1.5 tons of bagasse per hour. And using the fermentation strategy we devised last course, we came up with the number that we would get 15,000 liters per hour of fermentation broth. This is a process diagram that we devised for the process we made. We start with centrifugation, where we separate all the large particles of bagasse that are left in the media. Afterwards, we do microfiltration to separate like large molecules from the result from the output of the centrifugation. And afterwards, we go to a cation exchanger to remove impurities. The output from the cation exchanger goes to the anion exchanger, where we will trap the lactic acid in the resin because the output of the cation exchanger is at pH 5, and at pH 5 the lactic acid has a negative charge. Therefore, it will be bound to the anion exchange resin, and we can elute it afterwards to get a better purity. But in our case, that didn't happen. Most of the lactic acid went to the first flow through. However, like this would be a like different on the actual process. Most of the lactic acid would get bound to the column and would get eluted afterwards. However, after the anion exchange, we picked vacuum evaporation to concentrate our bioproduct. Then we have separation techniques. Centrifugation has the advantage of being reliable and doesn't consume extra materials. You just have your equipment and you use it over and over and over. Also, you have several mechanisms of centrifugation that are used by different equipments because you have like decanter centrifuges, you have tubular centrifuges, and you have like disc stack centrifuges. So you have these several modes or bases of separation of forced sedimentation and centrifugation. However, you have the disadvantage that as you scale up and up, these angular velocities are harder and harder to maintain and are more dangerous as the equipment goes larger. Next up, we have filtration. It has the advantage of simple operation. You just have the filter and whoop, well, that's dead end filtration, but you get the idea. We also have a variety of pore sizes and separation bases because most of filtrations have like a size exclusion, but some also have like donor separation where like the membrane is charged and it also separates by charge. Or you have like, for example, in reverse osmosis, which can be considered a kind of filtration where like you have like concentration differentials as a separation basis. And as disadvantages, we have these membranes, which are very like foul. They get foul with use, and they get blocked and they stop working. And also for chromatography, we have like several different separation mechanisms. For example, in size exclusion, we have like size with the beads with their different size porosities. We have ion exchanger with the mirror matrices of different charges. We have hydrophobicity interactions that separates like biomolecules based on their hydrophobicity, and we have affinity interactions, which are very, very interesting and very useful. For example, for molecules that have like metal ions in them, or like proteins that have histidine tags baked into them by their plasmids. But we also have disadvantages that it's hard to escalate due to the equipment, the size, very, very tall columns, and also due to reactant expenditure. On the topic of unit operation parameters, you can see on screen the formula that is usually used for scaling up centrifuges. You see like terminal velocity and sigma factor. Terminal velocity explains the parameters of the particles that you're trying to separate from your solution, while the sigma factor encapsulates all of the parameters that are like the size of the centrifuge, like the length, the inner radius, the external radius, the angular velocity, or also the the number of discs in the case of a disc stack centrifuge, or like even the angle of the discs. So all of this is parameters depending on the type of centrifuge. They will change the volumetric flow that the centrifuge can handle, as well as the sedimentation speed and the residence time. The sedimentation speed, if the sedimentation speed is lower than the residence time, then you can fully sediment the the solution. But if the sedimentation speed is higher, then it will get out not fully sedimented. So like the angular velocity, the radiuses, the disks, etc., they change the amount of cementation that you get in your final product. The type of centrifuge that you use also has some different criteria. For example, disk stack centrifuges and decanter centrifuges have very large capacities, can handle very large volumes, while tubular bowls cannot. However, tubular bowl centrifuges have very high capacity for centripetal forces. Like you can have like very high angular velocities with them, and not so much for the disk stack and the counter centrifuges, which are more in line with lower angular velocities. On the unit operations that we left out, we have ultrafiltration, which we intended to use to separate the smaller like biomolecules from the solution, for example, proteins, etc. And we didn't use it because in the lab, when we tried to do it on a ultrafiltration unit in the centrifuge, the filter got clogged up. Only a little bit of the liquid got past the membrane. Um, in this way, we concluded that the ultrafiltration would need a better design of the unit operation, perhaps a cross-flow mode of operation, so that the flow goes and the particles get separated, but you don't get so much cake on the filtration membranes. And in this way you can actually like adapt this operation for larger scale, because if you get so much cake and so much blockage on the filtration unit, like it's not gonna be sustainable to employ this unit operation. And we also proposed precipitation, but we didn't go ahead with it because you would need to add a precipitating agent, which would conclude a an impurity, and you would need several steps, one for precipitation, and you would need like some step ahead to like decouple the lactic acid from the precipitating agent. So since we wanted as few operations as possible, we didn't include it in our process.